Hello everyone. In this video we look at the motion of an object along a vertical straight line. So we also call this as motion of an object under the influence of gravity. Why? Because any object which is traveling in an straight line motion in the vertical plane will be experiencing the force of gravity. So when we look at what are these cases of vertical straight line motion, we can have an object thrown upwards from the surface of the earth. Now as we throw the object upwards, what we see is the initial velocity will be in the upward direction, but it will be experiencing an acceleration due to the gravity. And so we represent this with g. The value of this we will take it to be 9.8 meters per second square, or sometimes we can approximate it to 10 meters per second square. So as we see, this object will be under deceleration. So what happens is, as it starts climbing up, the velocity of the object will start decreasing, and eventually at some point it would become zero. Then the object would start falling back, or it will start falling downwards, and then it will eventually reach the surface of the earth. So this is what we'll be having in case of an object thrown upwards from the surface. The second case is a body dropped from some height with an initial velocity 0. Now dropping or releasing is one of the important the cases of motion that we look at, because if we are dropping an object from a standstill position, then the initial velocity of this would be taken as 0. So dropping or releasing from a standstill position, the initial velocity will be 0. Whereas if we drop an object from a moving body, let's say for example we have a balloon which is rising upwards, and we simply release a stone or something from the balloon, then the initial velocity of the stone will be equal to velocity of the balloon. So that is about the dropping or releasing condition. So generally when we say we are dropping an object from a height h, we will be looking at dropping it from a standstill position. So the initial velocity is going to be 0. And what we observe is though the initial velocity is 0, it is under the influence of gravity, which means it will have an acceleration g downwards, and it would be starting to accelerate in the downward direction, and then eventually it will be reaching the surface of the earth. The third case is a body projected vertically upwards from a height. Now in this case also, like we throw the body up, so initial velocity will be upwards, but this object also is under the influence of gravity. So what would happen is this body will be decelerating. It goes to a height where the velocity will become 0, and then from that position it will start falling down. And here in the problems that we are going to solve, we'll assume that the body will be falling to the surface of the earth. So we look at the specific case when we go into the details of it. And the fourth case is an object projected vertically downwards with some initial velocity from a height. So we look at a particular height, and the surface. We are looking at a case where we throw the body with an initial velocity u downwards, and here the acceleration due to gravity is also downwards. So we see that the particle is going to be increasingly changing its velocity, since the velocity and the acceleration are in the same direction, and then eventually it will be reaching the surface of the earth. So these are the broad cases that we have in case of motion along a vertical straight line. Now here we'll be having some assumption that when the objects are moving under the influence of gravity, we do not consider the air resistance. Now if we consider the air resistance, then the solving of the problems will become a little bit more complex. So for the simple cases that we are going to be dealing with, we assume that there is no air resistance. Means for the vertical motion of any body, in all the 4 cases we discussed, all the objects are going to be experiencing only one acceleration, and that is acceleration due to gravity. And we also assume that the small changes in acceleration due to gravity with height are neglected, because when we go to the gravitation chapter, we'll be able to understand that if we go to a relatively larger height from the surface of the earth, then the acceleration due to gravity g value will be changing, and same is the case if we are going down into the earth. So we'll discuss about those cases later, but here while we are solving problems in vertical straight line motion, we assume that the acceleration due to gravity is almost constant and it will not be changing with respect to height. So now we'll look at what is the sign convention that we'll be following in case of the vertical straight line motion. Now in horizontal straight line motion, if you can recall, what we discussed is since the motion is going to begin with the initial velocity, we have taken the direction of initial velocity to be positive, and any quantity in the opposite direction will be taken as negative. Whereas when it comes to the vertical straight line motion, we generally go with this sign convention. So anything upwards we take it as positive, and anything downwards we take it as negative. Since in all these different cases of motion, the acceleration due to gravity will be downwards, so we will be always considering a is equal to minus g, or if you look at the exact value, minus 9.8 meter per second square. Approximately we can even take it as minus 10 meters per second square. So this is the sign convention that we will be following. So any quantity, whether it is the initial velocity or final velocity or displacement, if they are measured upwards, they will be taken as positive, and if they are measured downwards, they will be taken as negative. Let us look at the first case where we are throwing an object upwards from the surface of the earth. So let us say the initial velocity of the object is u, and here we can see, since we are throwing it upwards, it will be in the upward direction, and the final velocity which we are looking at, where the object will be able to reach a maximum height h, will be 0. Why? Because as the object is climbing up, since it is under deceleration, as the acceleration due to gravity g is downwards, the velocity value will keep on decreasing and eventually it will become 0 at the maximum height location. So we'll try to find how much time it will take to reach the maximum height, and also what is the maximum height value. So let us just go and take a look at what are the variables that are given to us. So initial velocity is let us say given as u, and we take it as plus u because it is in the upward direction, and acceleration we'll take it as minus g since it is g in the downward direction, and final velocity will be 0 because we are looking at the maximum height position, and we want to know what is the time it takes to reach there. So initial velocity, acceleration, final velocity, and time. The equation that relates all these four variables will be v is equal to u plus at. So we have 0, final velocity is equal to initial velocity u plus acceleration is minus g into t. Now on rearranging, what we have is g into t is equal to u, so thereby t will be coming as u by g. So this is the time it takes for the object to reach the maximum height, and we want to calculate what is this maximum height value. Then we must look at the displacement. So the maximum height is nothing but the vertical displacement of the object when it is reaching the maximum height. So if you want to find the displacement, let us say the displacement is h. Why we are taking it as h? Because the displacement here is going to be in the upward direction. Now initial velocity is u and acceleration is minus g, final velocity is 0, displacement we are taking it as h. The equation that relates all these variables will be v square is equal to u square plus 2as, where s represents the displacement. So v square means final velocity square is 0 square is equal to u square, initial velocity square will be u square plus 2 into acceleration is minus g into displacement, here we are taking it as h. On rearranging, u square will come to the left side, it will become minus is equal to minus 2gh minus minus will be cancelled, u square by 2g is equal to h. So if we throw an object with an initial velocity u from the surface of the earth, then it will be reaching a maximum height which is equal to u square by 2g. So these are the two important results in case of the object thrown vertically upwards from the surface of the earth. Now when we look at the next example, which is an object which is dropped from static position or from an stable state where the initial velocity of the object will be 0. Now we know that this will be moving under the influence of gravity, which is downwards, so the acceleration is going to be downwards. So we look at what will be the time taken for the particle to come to the surface of the earth, and also what will be the final velocity value when it is reaching the surface of the earth. Now when we look at the motion of the object, it is initially at the top of the building and finally it is coming down to reach the surface of the earth. So the displacement here is measured in the downward direction. So the displacement value S in this case when it is reaching the surface of the earth will be minus h, and acceleration value will be minus g, initial velocity will be 0. From this we will try to find what is the time and also what is the final velocity. So first when we look at these variables s, a, u and t, we have the equation s is equal to ut plus half at square. So substituting the values, minus h is equal to initial velocity 0, so this term will become 0, half into a is minus g into the t square will come. So minus minus on both sides is cancelled. When we take the 2 to the left side, it will become 2h, it will go to the numerator. 2h is equal to gt square. From here we'll have 2h by g is equal to t square. This would imply the value of t, time taken to reach the surface of the earth, will be root of 2h by g. And the final velocity when it is reaching the surface of the earth, so if we look at s, a, u and v, so we have the relation v square is equal to u square plus 2as. Since the initial velocity is 0, this term will become 0, so v square is equal to 2 into acceleration is minus g into the displacement value, as we discussed, it will be minus h, where h is the height of the building, or the height from where we are dropping the object. So minus into minus will become plus, so 2gh. So v will be plus or minus root 2gh if we take a square root on both sides. Now as we know, since the final velocity will be in the downward direction, as per our convention we will take it as minus root 2gh. But if we are just looking at the magnitude part of it, the value magnitude will be root 2gh. So these are the important results in case of an object being dropped from a height h. So time it takes to reach the surface of the earth will be root of 2h by g, and when it comes to the surface, the velocity, final velocity value will be equal to root 2gh in the downward direction. The third case is an object which is projected vertically downwards with some initial velocity from a height. So let us say we have an object which is projected downwards with an initial velocity, and here we know the acceleration due to gravity is also downwards, and when it is reaching the surface of the earth, it will be having a displacement of h in the downward direction. So we'll try to represent the parameters that we already have. So initial velocity will be minus u. Why we are taking it as minus is because the object is projected vertically downwards, so the initial velocity is downwards, and acceleration value will be minus g since it is in the downward direction, and displacement value will be also equal to minus h, because the initial position is at the top of the building or the place where we are throwing the particle from, and the final position is at the surface of the earth. So the displacement is measured in the downward direction. And we would like to find what is the time it takes to come down and also the final velocity. So to find the time, so we'll use s is equal to ut plus half at square. In this s value will be minus h is equal to minus u into t plus half into minus g into t square. I mean both sides we can cancel the minus, so you will get h is equal to ut plus half gt square. Now we know this is a quadratic equation in terms of time, and by solving this we will be able to get the value of time. It might so happen that in some cases we'll get two values of time, and in the two values only one of them might be practically applicable. So whenever we are getting time value to be negative, we will be omitting it. And to find the final velocity, we'll use v square is equal to u square plus 2as relation. So v square is equal to initial velocity is minus u the whole square plus 2 into minus g into minus h. So thereby we'll have u square plus 2gh. So v value will be equal to root of u square plus 2gh. This is the final velocity of the object by the time it reaches the surface of the earth. So these are the two important results in case of an object which is thrown vertically downwards from a height. The fourth case we have is an object which is projected vertically upwards from a height h. Now as we have discussed, the object which is projected upwards with a velocity u from a building of height h will also be moving under deceleration, since it will be under the influence of gravity. Now as it starts climbing up, its velocity will become 0 eventually, and then it will start to fall down. So here the motion that we look at is eventually when the object is falling down, we assume that it is finally reaching to the surface of the earth. So the initial point is the position on the top of the building or height where we are throwing the particle upwards, and the final position is going to be the surface of the earth. Now when we look at the vertical displacement, initially we are at height h and finally we are at the surface of the earth. So the vertical displacement is going to be minus h, where h is the height of the building or the place where we are throwing it. Why we are taking it as minus is because it is going to be measured in the downward direction, and acceleration value will be minus g. Initial velocity, if we are throwing it with a velocity u, since it is in the upward direction, we will take it as plus u, and we can find what is the time it takes to reach the surface of the earth, and also we can find what is the final velocity. Now to find what is the time it takes to reach the surface of the earth, we can look at the relation s is equal to ut plus half at square, which means, so if you look at the equation s is equal to ut plus half at square, the displacement value for the overall journey is minus h is equal to initial velocity is plus u, so ut plus half into acceleration is minus g into the t square. So if you look at this, this again is an quadratic equation in terms of time. By solving this, we will be able to get the value of t. On the other side, to find the value of the final velocity, we will use v square is equal to u square plus 2as relation. In this, the final velocity square is equal to initial velocity will be u, so u square plus 2 into acceleration is minus g into the displacement is minus h. So again u square plus 2gh. So the final velocity value will be root of u square plus 2gh. Now we can see one interesting relation over here. Whether we throw the particle downwards with a velocity u, which we saw in the previous case, or we throw the particle upwards with a velocity u, in both the cases, by the time the particles reach the surface of the earth, their velocity value is going to be same. And again here, if we are to follow the sign convention, we would have taken it as minus, because the final velocity will be in the downward direction. But just to talk about the magnitude of it, we can say it is going to be root of u square plus 2gh. So this is about the motion of an object which is projected vertically upward from a height h. So we are considering that it will climb to the maximum height and then it will fall back to the surface of the earth. We look at some illustration problems to understand how we'll go about solving the problems in the vertical straight line motion. Let us say we have a ball which is thrown upwards from the top of a tower 40 meters height. So the height of the tower is 40 meters with a velocity of 10 meters per second. So the ball is thrown upwards. Now find the time when it strikes the ground. So we can assume that g is equal to 10 meter per second square. Now keep one thing in mind, if they are specifically giving in a problem to take the value of g to be either 10 or 9.8 meter per second square, we have to go with that value. Otherwise, while solving numericals in the competitive examinations or even in the regular exams, we will have to consider the value of g is equal to 9.8 meter per second square unless they specifically mention it. Now we'll just take a look at this question. So we are throwing an object upwards with a velocity of 10 meters per second from a building of height or tower of height 40 meters. Now as we already discussed the case of this motion, it will go up, reach the maximum height and then it will fall and then it will be striking the ground. In the overall journey, if you look at the displacement s, it will be equal to minus 40 meters since the initial position is at 40 meters height from the surface and final position is the surface of the earth. So displacement is measured in the downward direction, so it will be minus 40. And the initial velocity u, since it is projected upwards, we will take it as plus 10 meters per second. Acceleration, since it is in the downward direction, it will be minus 10 meters per second square. We need to find the time when it strikes the ground. So the variables here are s, u, a, t, and the equation that relates all the variables is s is equal to ut plus half at square. So s value is minus 40 meters is equal to u is 10 meters per second into the t plus half into a is minus 10 meters per second square into t square. Now since all the variables are in the SI unit, when we solve the value of t, it will be coming in seconds. So for now we'll just omit the use of these units so that we can just do the calculation in terms of numbers. Now be careful while we are solving problems, we have to check before we are omitting these units and just going into the solution with numbers, that all the variables are in the same system of units. Like in this case, everything is already in the SI system. Now the equation we have over here is minus 40 is equal to 10t. So 2 1s are 2 5s, so it will be minus 5t square. Now on both sides we can divide with 5, so you will get minus 8 is equal to 2t minus t square. We'll try to bring the terms on the right side to the left side, so they will become minus, which means the minus t square will become plus and 2t will become minus 2t. So the final expression we are going to have is t square minus 2t minus 8 is equal to 0. Now when we want to solve this, it is a quadratic in terms of t. We can try and factorize it. T square minus 4t plus 2t minus 4 into 2 is equal to 0, and when we factorize it, we will get t minus 4 into t plus 2 is equal to 0. From here we have either t is equal to 4 seconds or t is equal to minus 2 seconds. Now this t is equal to minus 2 seconds is not acceptable to us, though mathematically this solution is possible. Practically, since the time cannot be negative in all the study of motion, t minus 2 will not be acceptable. So the correct answer is t is equal to 4 seconds. So when you throw the ball upwards with a velocity of 10 meter per second from a tower of 40 meters height, the time it takes to reach the surface of the earth, or the time it takes to strike the ground, will be 4 seconds. Let's look at one more problem. a stone is thrown vertically upwards with a velocity 30 meters per second. So if the acceleration due to gravity is 10 meters per second square, which means in this problem we can take g is equal to 10 meters per second square. What is the distance traveled by the particle during the first second of its motion? Now, this is where whenever they talk about the distance in case of the straight line motion, we need to be careful whether there is a change in the direction of motion or not. So they're talking about first second of its motion. We will first try to find, because we already have a result. If you throw an object vertically upwards with a velocity u, then the time it takes to reach the maximum height will be u by g, because this result we have seen in the derivations. So u value is 30 meters per second divided by g value here, we can take it as 10 meter per second square. So the time is coming as 3 seconds. So if you are throwing an object with this velocity of 30 meters per second, then it is reaching the maximum height in 3 seconds time. So during the first second of journey, it will be having no change in direction of motion, which means the displacement value will be equal to distance covered, the magnitude. So the nth second displacement formula we have, Sn is equal to u plus a by 2 into 2n minus 1. Now this formula can be used for all the straight line motion, whether we have the horizontal straight line motion or the vertical straight line motion. So here the values that are available with us are the initial velocity u is equal to plus 30 meters per second since it is in upward direction, and the acceleration a will be equal to minus 10 meter per second square since it is in the downward direction, and the value of n is the second, the nth second basically. So here n is equal to 1. So the Sn value will be 30 plus a is minus 10 by 2 into 1 minus 1, which will be 30 minus 2 1s are 2 5s are minus 5. Inside the bracket we have 2 into 1 is 2, 2 minus 1 is 1. So totally we have 25 meters. Now all the other variables are in the SI system, so the displacement in the nth second will be in meters. Now this nth second is basically here the first second. This is going to be the value of the distance covered. So the distance covered in the first second of the journey will be equal to 25 meters. Now in whichever straight line motion we talk about the distance, we have to be careful to understand if the particle is having a change in the direction of motion or not. If there is no change in the direction of motion, then the magnitude of the displacement will be equal to distance covered. If there is a change in direction of motion, then we will have to work out the problem accordingly. In fact, in horizontal straight line motion, we have even discussed some examples of this. Let us look at one more question. We have a ballast bag dropped from a balloon that is 300 meters above the ground and is rising at 13 meters per second. So this is a case where when we are dropping an object from a moving body, the initial velocity of the object will be equal to the velocity of the moving body, and the time before the bag hits the ground. So we need to find how much time it takes for the bag to hit the ground. So we have a balloon which is rising at a speed of 13 meters per second, and we are releasing a ballast bag from that. So the initial velocity of the ballast bag will be same as the velocity of the balloon, which means it will be upwards 13 meters per second. So we take it as plus 13 meters per second, and here they are giving the value of g to be taken as 10 meter per second square. Since this will be moving under the influence of gravity, so g will be downwards. So as per our sign convention, anything downwards we take it as negative. So acceleration of this ballast bag once it is released from the balloon is going to be minus 10 meters per second square, and the ballast bag will raise because its initial velocity is upwards, and it will eventually fall back to the ground. Now when it is falling back to the ground, the initial position where it is released is 300 meters above the surface of the earth. Now when it is hitting the ground, the overall displacement of the journey from the initial position where it is released to the final position, which is the ground, the overall displacement for the journey will be equal to minus 300 meters. So we need to find the time it takes to hit the ground. So we'll use S is equal to ut plus half at square relation, which means minus 300 is equal to, since all these variables are in the SI system, so we will omit the use of units and we'll just do the calculation in terms of numbers. Minus 300 is equal to u is 13, so 13t plus half into a is minus 10 into the t square. So what we have is minus 300 is equal to 13t minus 5t square. So we'll bring the terms on the right side to the left side. So what we'll have is the minus 5t square will become plus 5t square, and the 13t will become minus 13t. So the final expression we have is 5t square minus 13t minus 300 is equal to 0. Now this is a quadratic in terms of time. If you look at this with the standard quadratic equation, ax square plus bx plus c is equal to 0, the roots of this are going to be the roots of the quadratic equation are going to be x values will be equal to minus b plus or minus root of b square minus 4ac by 2a. Now here the value of a is 5 and b is minus 13 and c is minus 300. So if you substitute the values of a, b and c, then the time will be coming as t is equal to 13 will have plus or minus root of 165 plus 6000 by 10, but we will omit this minus because that will be giving us a time value negative. So that possible value of time is 13 plus root of 6165 by 10. On simplifying the value, we'll get it as 9.15 seconds. So when we release the ballast bag from the 300 meter height, it will take 9.15 seconds to hit the ground. So we have one more question. A stone falls from a balloon that is descending at a uniform rate of 12 meters per second. Now in this case, we have the balloon which is descending or coming down with a speed of 12 meters per second. The displacement of the stone from the point of release after 10 seconds. So we need to find the overall displacement from the point of release. So this is where it is released after 10 seconds. So here if we take the value of g to be 10 meters per second square, then the acceleration will be 10 meters per second square downwards. Time of motion here is given to be 10 seconds. So since we need to find the displacement, we'll use S is equal to ut plus half at square formula. Now in this, if we consider the parameters along with the sign convention, the initial velocity value u will be minus 12 meters per second since it is in the downward direction, and acceleration value will be minus 10 meters per second square since it is also in the downward direction, and time given to us is 10 seconds. So we need to find the displacement value. So on substituting the values, we will get S is equal to minus 12 into 10. So we are just taking the numbers, omitting the units because everything is already in the SI system, plus half into a is minus 10 into t square. T square will be 10 square. So minus 120. So this will be 2 ones are 2 5s minus 500, which is going to be minus 620 meters. Now here we have taken the value of g to be equal to 10 meters per second square. the displacement is coming as minus 620 meters, which means it will be 620 meters downward, the final position downward from the point of release. The reason why I've explained this by taking the value of g to be 10 meter per second square is, if you look at, the conclusion will be the value of the displacement for us is coming as 620 meters. But we see that in the options, the 620 meters is nowhere to be there. So this question, they have not given the value of g. So whenever they don't give the value of g, it is always advisable that we'll take the value of g not as 10 meter per second square, but we take it as 9.8 meter per second square. So instead of g equal to 10, if you take it as 9.8, then the acceleration would be minus 9.8 meter per second square. And we'll just try to do the problem by having acceleration is equal to minus 9.8 meter per second square. So s is equal to ut plus half at square, which means u is minus 12 into time is 10 plus half into a is minus 9.8 into t square is 10 square. So minus 120, this is 2 ones are 2 4.9s minus 490, which will be equal to minus 610 meters, which means the displacement of the particle from the point of release is minus 610 meters, which means the stone would have come down by 610 meters from the point of release. So the option for this question is C. Now this is exactly the reason why if they don't give the value of g, we have to take the value of g to be 9.8 meter per second square and not 10. And if we take it as 10, we'll get almost closer value, but it will not be the exactly same answer. So in case you want to continue solving problems with g is equal to 10 meter per second square, you can do it so, but that is only acceptable in the case of the competitive examinations. But you need to be looking for not the exact answer you get, but an approximately closer answer to that. So this is about the kind of problems we can have in the vertical straight line motion. Now there is another important model of question in the vertical straight line motion, that is about the meeting condition. Now what we mean to say by the meeting condition is, let us say we throw an object upwards from the surface of the earth, and at the same time we release another object. So object 1 is thrown upwards from the surface of the earth, and object 2 is released. So initial velocity for this is going to be 0. Let us say the height of the second object is h from the surface of the earth. Now these two objects, this will start climbing up, whereas the second object will start descending. At some point in between, these two objects will be meeting. The questions will be as to find at what time they will be meeting, or at what vertical height from the surface of the earth, or at what distance from the top of the building these two objects will meet. These kind of questions are what we call as the meeting condition problems. Now what we have seen just now is the case 1 or first case of the meeting problems. The second case will be, we'll throw an object upwards from the surface of the earth. The second object will also be thrown downwards, which means this has some initial velocity which is in the downward direction. In this case also they both will be meeting at some point, and we can find out what is the time at which they will meet and even the position where they will be meeting. This is the case 2. The case 3 will be, we throw the object from the surface of the earth, the first object, and the second object we throw it upwards from the height. What would happen is, this will be initially ascending, and after reaching the maximum height it will start coming down. In this case also the two objects might be meeting at some point. The point where they would meet depending upon the values of the velocities and even the height of the building from where it is thrown. But these are the three broad cases that we have in the meeting condition problems. Now we'll try and take a look at a couple of models of questions in these meeting condition, because in competitive examinations very often they do give the problems on the meeting condition, both in horizontal straight line motion as well as vertical straight line motion. Let us look at a case where a stone is released from the building of height 200 meters, which means that the initial velocity of that will be 0. At the same time, another stone is thrown upwards from the surface of the earth with a velocity 30 meters per second. The question is, after how much time they both will meet? So here they are giving the value of g to be taken as 10 meter per second square. Now we'll just try to represent this over here. So we have the first stone which is released from the top of the building of height 200 meters, which means the initial velocity of this is going to be 0. We'll call it as the first object. Now the height of the building is given to be 200 meters. Same time, the second object is thrown upwards with a velocity of 30 meters per second. Keep one thing in mind, both of them are under the influence of gravity, which means the acceleration of the first object as well as the acceleration of the second object will be g downwards. Now let us say the meeting point is at a distance x from the surface of the earth. Then the distance of the meeting point from the top is going to be 200 minus x. So x is the distance of the meeting point from the surface of the earth. Now we'll try to look at the motion of the first particle and motion of the second particle separately and try to use the meeting condition. For the first particle, the initial velocity is 0, acceleration is g downwards. We take the g value to be 10 meter per second square. So here for the first particle, u is equal to 0, a is equal to minus 10 meters per second square, and time we are fixing it as t is the time at which they both will meet, and the displacement from the initial position to the final position will be minus of 200 minus x. Why we take the displacement to be negative is because it is in the downward direction. The length of this particular distance is 200 minus x, but since it is measured in the downward direction, we'll take it as minus of 200 minus x. Now when we use the equation s is equal to ut plus half at square, what we'll be having is minus of 200 minus x is equal to, u is 0, so this term will become 0, half into minus 10 into t square. So we can cancel both sides minus, so what we'll have is 200 minus x is equal to 5t square. So let us keep it as equation 1. Now let us look at the motion of the second particle. So by the time the second particle is meeting the first particle, it is climbing up through a distance x, which means the displacement will be plus x, and acceleration of course is minus 10 meters per second square, and the initial velocity of this is plus 30 meters per second since it is projected upwards, and the time of the journey is again t, because both of them will be in the journey for the same time. Here we will use the equation s is equal to ut plus half at square to relate the variables. So what we'll have is x is equal to 30 into t, because the initial velocity is 30, plus half into minus 10 into t square, which means x will be equal to 30t minus 5t square. This is equation 2. Now what we do is we will take the value of x from the second equation and substitute in the first equation, because we are looking to solve for the value of time. So by bringing the value of x from the second equation and substituting in the first equation, what we have is 200 minus x value will be substituted as 30t minus 5t square is equal to, on the RHS we already have 5t square. So 200 minus 30t plus 5t square is equal to 5t square. Now the 5t square and 5t square will be cancelled. This gives us 200 is equal to 30t. From here we'll get the value of time to be 200 by 30, which is equal to 20 by 3 seconds. So this is the time after which both these stones will be meeting. Now we look at one more question in a similar model. So we have an object thrown downwards from the top of a building of height 300 meters with a velocity 20 meters per second. At the same time, another object is thrown upwards from the surface of the earth with a velocity 40 meters per second. After how much time they both will meet? This is a different case of the meeting condition problems we have looked at. And in this problem also they are saying the value of g can be taken as 10 meters per second square. So we look at this question. So here the first object is thrown downwards with a velocity of 20 meters per second. The height of the building from where it is thrown is given to be, in this case, 300 meters. Now the second object is thrown upwards with a velocity of 40 meters per second. And as we see in case of vertical straight line motion, both the objects will be meeting under the influence of gravity, which means the acceleration of both the objects will be g downwards. Now we look at the case where they both will meet. Let us say again, like the way we have talked about in the previous problem, the meeting point is at a distance x from the surface of the earth. Then the distance of the meeting point from the top of the building is going to be 300 minus x. So we look at the motion of the first particle. Initial velocity is 20 meters per second downwards. So we have to take it as minus 20 meters per second. Acceleration is g downwards minus 10 meters per second square. And displacement is nothing but the 300 minus x is the distance covered, but it is covered in the downward direction. So it will be minus of 300 minus x. And the time of the journey is t. So we'll have the equation s is equal to ut plus half at square, which means minus of 300 minus x is equal to u into t minus 20 into t plus half into minus 10 into t square. So we see that there is an overall minus on both sides which we can cancel. So leaving 300 minus x is equal to 20t plus 5t square. So we can cancel 2 1s are 2 5s. So this is the equation we have. We can call it as equation 1. Now let us go to the second particle motion, which is the particle that is thrown upwards from the surface of the earth. So for this, as it is climbing up to meet the second object, the displacement is going to be positive plus x. The initial velocity of this, which is 40 meters per second, is also in the upward direction, so it is going to be positive. But the acceleration of this also is the downward direction, just like the first particle. So it will be minus 10 meters per second square. And the journey time is t. Here also we have s is equal to ut plus half at square as the relation. So x is equal to ut, which is 40 into t plus half into a is minus 10 into t square, which means it will be 40t minus 5t square. Now from this equation we have the value of x is equal to 40t minus 5t square. We can take the value of x and substitute in the first equation. So if you substitute the value of x to be 40t minus 5t square, what we will get is 300 minus, in place of x we are substituting 40t minus 5t square, will be equal to 20t plus 5t square. This will give us 300 minus 40t plus 5t square is equal to 20t plus 5t square. On both sides the t square term will be cancelled, so we'll have 300 is equal to minus 40 on taking to the right side will become 60t, because 40 plus 20 will be 60, which means t will be equal to 5 seconds. 300 by 60 will be 5. So after 5 seconds both the objects will be meeting each other. So these are the kind of questions we can have in the meeting condition. So meeting condition, basically we are trying to relate the displacement of the both the objects, because the position of the meeting position basically will be relating to the height of the building or the place from where we'll throw the second object. So this is what we have in the vertical straight line motion.